Hello and welcome to our paper's presentation. My name is Joshua Rego and I'll be presenting the work in our paper titled Robust Lensless Image Reconstruction via PSF Estimation. Several computer vision applications can benefit from greater visual information while keeping camera cost and size low. Tiny robotics, for example, can greatly benefit from this. As robots get smaller, lens-based cameras become less feasible to use. Lensless cameras can be a promising option. Getting rid of the lens allows for a near-flat form factor, as the mask can be placed much closer to the sensor, as shown here. It also allows for lower cost and construction complexity with fewer parts to configure and account for. Some prominent traditional methods include flat cam, that implements a coated mask with transparent and opaque features that diffract light to cause unique shadows on the sensor. Diffuser cam utilizes a diffusion layer as the mask that diffuses light from the scene onto the sensor. The problem with traditional reconstruction methods is that they still need some known information from the camera model. This may be in the form of a point spread function or a coded mask, which may not always be available or may have variations. Traditional reconstruction is also a very slow iterative process and may still produce low-quality reconstructions relative to lens-based cameras. There are also some deep learning approaches that have been used. The one at the top right uses the flat cam model and utilizes adversarial learning to improve reconstruction quality, while the bottom right uses the diffuser cam model and implements a learned ADMM and UNet to improve reconstruction quality. These papers show that deep learning approaches can drastically improve reconstruction quality. However, they are still limited by the need for prior information from the camera model, or instead learn the mapping for a single PSF. This doesn't generalize well for variations in the PSF and may require additional training for each new camera. For our paper's contributions, we show the design of a GAN-based network to reconstruct lenses images at high quality. We implement a model that can generalize to multiple PSF variations by estimating the PSF in the training pipeline. We also verify our model on real and synthetic datasets to analyze the model's ability to generalize reconstruction to PSF variation. Our approach feeds the input image into two separate generators, one for the image reconstruction and the other for PSF estimation. Both outputs also have their own discriminators that are trained on the Wasserstein distance. We then feed both the output images to a forward convolution block to estimate the input lensless image again and generate a consistency loss used for both generators. To create the synthetic dataset, we generate 20 variations of the original diffuser cam PSF and convolve the lensed images with each of the PSF variations. The figure shows two examples of PSF variations and their corresponding synthetic lensless images in the center two rows, while the original PSF and lensless images are shown in the last row for comparison. The qualitative results for the original PSF show that our method in column B can achieve results on par with the state-of-the-art method in column C. This is done without the need for the PSF at test time. We also see from the drop in quality of the horse image for our method that there is a noticeable trade-off for single PSF reconstruction quality versus generalizing to multiple PSFs. The quantitative results as well show competitive performance with the state-of-the-art method. While our method is slightly lacking for the SSIM metric, it shows a slight improvement in PSNR while performing reconstruction with a considerably faster inference time. For PSF estimation, the model can estimate the PSF quite closely to the true PSF with small deviations. The PSF variations are reflected with slight variations in the image reconstruction quality, but the network is largely able to generalize and reconstruct them fairly well. We also perform a noise abolition study to show the effects of additive Gaussian noise and can see that all models quickly degrade in performance with even small variance values of Gaussian noise. Fine-tuning our model to train with varying levels of noise greatly improves this, as shown in the graph by the dashed and dotted line. In addition to the synthetic dataset, we capture an additional lensless video dataset using 3 different PSFs. These are some images of the mirrorless camera and diffusion mask mount that we used. While the results are not as high in quality as the diffuser cam dataset, we still see plausible reconstructions with regions that resemble the target image in column C. For comparison, in column B, we also show the results of the ADMM algorithm on this data. We believe that this is primarily due to the diffusion layer used, which has a much larger spread of light than the original diffuser and causes more dense caustics as seen in column E. To conclude, we show that better generalization of lensless reconstruction for PSF variation can be achieved through a PSF estimation method. We verify our approach on real and synthetic datasets to show on-par performance to the state-of-the-art, without the need for the PSF at test time. We also note challenges to our method for sensitivity to input noise and a need for high-quality PSF caustics as shown by the real data. There are several avenues for future work to make lensless imaging more robust and useful. This includes unsupervised or self-supervised methods so that ground truth PSFs are not needed in training. Additionally, high-resolution reconstruction and video reconstruction may help expand applications for lensless cameras as well. Our team would like to thank Celine and Yasser for their help on this project and acknowledge the grants and resources that supported this work. Thank you all for watching.